invited me to present. A lot of fun. So I guess I'll get right into it. I'm here to talk about a couple different things that we sort of generally have dubbed PyCubed in my lab. As Kai's mentioned, I was at Stanford for the last couple of years and recently just moved to Carnegie Mellon back on the East Coast. And here's a couple of things we're working on. So first off, I'd like to just give a little background on where I came into the small sat arena and where a lot of this stuff came out of. First, this is a picture of PhoneSat 2, which is a project I worked on and as a grad student back in like 2012, 2013. Really innovative project. It was a CubeSat built around an Android smartphone. And yeah, this was a great thing to work on and sort of my entry point into small satellites generally and the first thing I ever worked on that flew in space. So lot of cool things here. I then sort of went off and did, as a grad student, the project I'm probably most known for, which is CubeSat. This is a picture of CubeSat, actually, and this is the ChipSat stuff that Kai's mentioned. I won't talk a ton about it, but just wanted to point out that the bus down here, this sort of bottom third of our 3U CubeSat, was actually a PhoneSat. So the guts of this bottom part of CubeSat were actually the same guts as in the PhoneSat here. So the reason I mention this is, well, I guess we'll get into that. So this is CubeSat. CubeSat flew actually finally successfully last year. This is artist rendering of what we did. We flung out a bunch of these little tiny 4-gram ChipSats, about 100 of them in LEO, and we're able to get signals from them, which is kind of the point. Here's the real video of this getting deployed on orbit. Unfortunately, we don't have video of the deployment that I showed in the last video, but this is the last video we have of CubeSat getting kicked out on orbit. So the thing I do want to mention about this, so ultimately we were successful here. We got this to work, but we ran into a bunch of problems along the way, and a lot of those problems had to do with avionics and sort of all the electrical and software pieces of the puzzle that you need to put together a small satellite like this. This is a picture of the Stanford dish, which is a famous, old radio telescope behind Stanford's campus. And the reason I show this is early on in our mission, we had a bunch of trouble making contact with the spacecraft, with the CubeSat, CubeSat. And what we kind of figured out eventually was that there was an antenna deployment failure. The folded dipole antenna, the tape measure, antennas that we all know and love. We had some trouble with that deploying, and as a result, the radio was signals were super quiet, and we had a hard time closing the link. Ultimately, we were able to get access to this giant dish, which had enough gain that it didn't matter, and it kind of saved the day for us. But there were some hard-won lessons from CubeSat that we took and tried to make improvements, right? And the result of that was PyCubed. So this is our avionics board for the satellite. This has sort of flight computer, EPS, electrical power subsystem functionality, comms functionality, and in fact, ADCS stuff that I'll get into in a bit. But this is actually, basically, we ripped out the guts of CubeSat, made a bunch of improvements based on our experiences over the years with that spacecraft and some of our flight experience, and then sort of repackaged the avionics on a single board, which is this is the CubeSat version of it that you see here. And this is all out there, open source. You can sort of download the schematics on GitHub and make your own. And the other thing that I'll mention is that the source of the name PyCubed is actually the fact that this board runs Python natively. It's running a distribution of Python called CircuitPython that's right now primarily being sort of developed and maintained by Adafruit, the sort of hobby electronics company. But it's a pretty amazing piece of software in that it's a Python interpreter that runs on sort of the bare metal on a small microcontroller. And you can basically plug this into your computer with a USB cable. It mounts as a flash drive, and you can pull up a Python REPL. So you can basically drag and drop .py files onto the board and then run them in real time and interact with the board in real time. It also supports code uploading via the radio. So we can upload new Python files and execute them on the board over the radio, i.e. on orbit. You can update your code. There's a lot of really great things about this. Namely, you don't have to write C or assembly code for your microcontroller anymore. And there's a bunch of sort of guardrail sort of training wheels in place with Python that you don't get in low-level C, like exception handling and garbage collections. You don't have to worry about pointers and low-level memory stuff. And it's generally a much safer programming environment for, say, aerospace, mechanical engineering folks who aren't expert software engineers. So plug for PyCubed. So now we'll get into some of the projects we're now working on based on this hardware and software platform. The first one is sort of a topic that's near and dear to my heart as a sort of trained GNC engineer, is attitude control. So I think I showed this plot last year, but the gist of this one is the actuators that are used to do attitude control on a spacecraft, classically reaction wheels and control moment gyros, or CMGs, so-called momentum actuators, basically flywheels, right? You spin the wheel one way and the spacecraft spins the other way. These things, it turns out, don't scale down to small spacecraft very well. So this is a picture of one of the CMGs from the International Space Station. And it looks huge, but it's only maybe 1.5 meters across. And 4 of these are what steer the ISS, which is massive, right? A couple of football fields across. So as a fraction of the overall size of the spacecraft, it's pretty tiny. So this plot is showing the fraction of the spacecraft mass taken up by these actuators versus the overall spacecraft mass. So for ISS, it's something like 0.2%. And as you go down the size scale, like a GeoComSat that's the size of a small airliner, it's maybe 1 or 2%. For what's classically considered a small sat, like an Earth imaging spacecraft that's like refrigerator sized or car sized in LEO, it's maybe 5 to 10%. And when you get down to the CubeSat scale, we're talking 30 to 50%, even more if you're talking a 1U CubeSat. So getting down to the PocketQube scale up here, we're talking about most of your PocketQube being taken up by your attitude determination and control hardware. And there's not a lot of room left over for payload or to do anything interesting, right? So we thought a bunch about this and came up with an idea that's not totally new, but we're taking a new spin on it. So that the idea is based around these actuators called magnetic torque coils, which probably some of you have heard of. These are basically electromagnets. Here's a picture of one, just a wire coil. And in fact, now we build these into the solar panels as a PCB tray, so they take up basically no space. And what they do, you run a current through the coil, it generates a magnetic moment, M, and that interacts with the Earth's magnetic field, the B over here. And here's a kind of cartoony picture, and that generates a torque. So the problem with this, these have been used for decades for what's called momentum dumping, which is offloading momentum, angular momentum from your reaction wheels. But they're under actuated, meaning you can only ever get 2 degrees of freedom of control because of this cross product-y thing here. So this says that you can only get torques that are in the direction perpendicular to B, the local magnetic field vector. So this means you can never actually get control in that third direction parallel to the B vector, the local magnetic field vector. So this has always been a problem. What we did, though, is if you take a look at this picture, right, it's pretty obvious that if you're in basically any kind of Earth orbit, this B vector is moving around a whole bunch as you go around the Earth, right? It's pointing in different directions in different places over the Earth. So it turns out if you're a little bit clever and you have a map of this magnetic field, and you know where it's going to be along your orbit ahead of time, you can solve a planning problem. And sort of over several minutes along your orbit, as B moves around, you can take advantage of that movement of B to get whatever torques you need over time. So you have to sort of look ahead and solve this more complicated planning problem. Thankfully, in my lab, this is egregious math, apologies for the math, but we do a lot of this kind of control trajectory optimization math stuff. Basically, we set this planning problem up as an optimization problem, and you can mostly ignore this. The basic idea is you turn this into an optimization problem that you can solve numerically, and we build custom solvers to do this. There's a few wrinkles, though. It turns out when you do this for attitude, i.e. pointing, rotations, it's a little more complicated. The math gets a little hairy, but we've done that. We've done things on quad rotors like this, 𝗖𝘁, so we know how to do that. We have sort of secret sauce for doing that. And essentially, we've developed a custom solver that can do this on the microcontroller that's on PyCubed, written in Python, et cetera. And this is kind of a cartoon simulation picture of that working in a simulated low Earth orbit. You can see the satellite doesn't simply rotate via like what's called an eigenaxis rotation, or the shortest path from the initial attitude to the goal attitude. It actually does this funky nodding motion, and that's this is sped up, I should say. This whole thing takes really, in reality, about 4 or 5 minutes, but it's taking advantage of this movement in the B vector and kind of doing this funky more complex motion to take advantage of the known magnetic field map to get where it needs to go, right? So we've done this in sim, and we built a PocketQube, PyCubed-1, which is shown here, to try to actually demonstrate this on orbit. This was supposed to be flying this time around with 𝗨𝘀. Unfortunately, we also ran into some licensing situations with the FCC that have prevented us from integrating this time around. So we're still going to try to do this, though, hopefully in 2021 with 𝗨𝘀. I should mention also this has a camera in it. So the idea here was to point the camera at the Earth, take some pictures, and kind of demo this 3-axis attitude control capability. So this is kind of fun. I'll just tease also a couple more crazy attitude control things. So this is very useful for gross pointing and large angle maneuvers. Unfortunately, because of that under actuation, right? Because you can never actually control that 3rd degree of freedom at a given time. This isn't super accurate. We think we can get within maybe 5 degrees pointing, which is perfectly adequate for a lot of applications like pointing antennas at the ground or pointing your solar panels at the sun, but it's maybe not good enough for certain fine pointing like imaging applications. So we have some other ideas for how to do that. Inspired by nature. So I love these videos of geckos. Turns out they're able to swing their tails around and arbitrarily reorient their bodies in midair like this. And these guys are, in fact, a lot smaller than the satellites we work on. Or they're about the CubeSat scale. They're a lot smaller than the PocketQubes. These guys weigh 4 or 5 grams. So we've taken inspiration from this and looked at what if we put tails on our satellite? And this is a quick simulation demo of that sort of idea, where we have 3, call them arms, if you like, attached to a slightly bigger satellite. And the idea here is that if you're trying to do, say, telescope pointing, this can actually get you extremely accurate fine pointing stuff, like on par with the best reaction wheel-based systems, while not taking up any internal volume, right? The idea is you would fold these arms down along the satellite externally and then deploy them on orbit, sort of like you deploy your antennas. And the reason this works is that the arms have much, much larger inertia than a little tiny wheel would that's stuck inside the satellite. So this actually lets you do, it gives you more actuator capability, right? Okay, so that's one of the things we're working on, and I'll briefly talk about one other thing we're working on based around these PyCubed avionics. This is a mission called VREX that we are in fact flying this December. It's 3 CubeSats that are going to talk to each other and sort of form a mesh network and do some swarm flavored stuff on orbit. And here's the really fun part about this. So the radio on PyCubed is a LoRa radio, and I know many of you guys in the PocketQube community have played with LoRa. One interesting thing, though, in the latest generation of S-band LoRa chips is that they support RF ranging, time of flight ranging between nodes out of the box. And the accuracy is pretty good. It's sort of sub-meter resolution that you can get out of this if you do some calibration. So we have these satellites. They can talk to each other with these LoRa radios, and they can actually measure the range between each other to pretty high accuracy over, say, 100 kilometers, to sort of sub-meter precision. So we're going to try to use this for navigation. And this is a really interesting problem for the following reason, right? So let's say we've got these 3 satellites. They can all measure the range between each other, right? And this is all you've got, right? And you want to figure out where everybody is. The problem here is if just having this range information, there's an ambiguity. You don't know, you know sort of the shape of the formation or swarm, but you don't know which way that swarm is oriented in sort of globally, right? So you know where, they're all this distance apart, but you could arbitrarily rotate and translate that triangle, and you can't tell the difference with just this range information. So you need something else to break this ambiguity to figure out where everybody actually is, right? And there's a couple of classic options. One is to talk to another spacecraft that has a known position, and that can sort of disambiguate this, right? A classic example of this would be GPS. The reason we're not using GPS here is, as you may have guessed from the moon background, one of the ideas here is that this is sort of a stepping stone towards future lunar constellations where you wouldn't have access to GPS. Another option would be to talk to something on the ground, right? And that has a known position. And this is classic, ground-based orbit determination. But we also similarly don't want to rely on ground assets if you're going and doing this around, say, the moon or some other solar system body that doesn't have infrastructure already. So what we're actually going to do here is something kind of different. We're actually we're going to rely on the complicated and messy gravitational field, in this case of the moon. It turns out we have super accurate maps of the moon's gravity field. They're accurate to better than 5 kilometers. In fact, the moon's gravity field is the best mapped, best known in the solar system, even better than Earth. And that's because the moon has no atmosphere. So you can actually fly super low down to the surface within sort of kilometers of the mountain peaks. A mission did this a few years ago called GRAIL. They took 2 spacecraft with precise ranging in between them and flew them in an orbit one behind the other. The idea is when one sort of flies over a mass concentration, there's a little bit more gravity, so it gets tugged a little more and speeds up a little bit, so the range increases. And then when the second spacecraft goes over the same spot, it sort of catches up, right? So there's this time varying range between the satellites that depends on the gravity field. And if you have really accurate ranging, you can back out the gravity field from this. So we're basically turning this idea around. We have the really accurate map from GRAIL, and we're going to measure the range between our satellites. And knowing the map, we're going to basically flip it around and go the other way. We're going to take the ranging data and the map and try to infer where we are globally. And it turns out we've done this in sim, and it works. And we think we can localize to within a few kilometers with this sort of technique. So we're going to do this on VREX in low Earth orbit coming up. This is flying in December, and hopefully we'll demo this ranging stuff in the next few months. And so that's kind of a couple of our projects. And I wanted to briefly, before I end here, plug the people actually doing all the hard work here. These are my grad students. The first guy here is Max Holliday, who's the real sort of brains behind PyCubed. PyCubed is basically his brainchild. He's done all the really great electrical engineering that's in there. There's a ton of good stuff in there, by the way. There's all kinds of fault tolerance stuff and stuff that's designed for enhanced radiation tolerance. It's really great. You should check it out. Kevin Tracy over here is our sort of GNC lead, who's doing all this navigation and magnetic torque coil based control. And then down here, this is Andrew. He left our lab this summer to go work at SpaceX, but he sort of did the initial work on this magnetorquer only attitude control stuff and wrote the first paper on it. And then these two guys, this is Brian and Taylor. They're our sort of optimization gurus who write all our solver stuff. So all the complicated math behind how to actually do that trajectory optimization stuff, these guys did all that. And with that, this is where you can find me and our lab. This is our GitHub. You can find all our schematics, code, et cetera, for everything. It's all open source. Here's our website, roboticexplorationlab.org. And love to take questions.